Hi, this is Mrs. Villette, and this is the video for period changes when solving trigonometric functions. I'm going to walk you through the idea behind the general strategy when there is a period change. And by period change, I mean we have some sort of omega or some sort of coefficient modifying the variable inside the trig function. So here's the idea behind how we're going to approach period changes. We are going to substitute what I'm calling a dummy variable. Then we're going to solve for the general solution using that dummy variable as if we're on the unit circle, then we'll back substitute. Let me show you how this works with an example. We have this first equation, 2 sine of 2y equals 1, and we want to solve for y in the interval 0 to 2 pi. So our first step is going to be our dummy variable substitution. So we are going to let 2y equal whatever you want to call it. In this case, I will call it theta. So my equation now looks like 2 sine of theta equals 1. I'm going to keep that theta in red to remind me that I need to do the back substitution at the end. Now I go about my normal strategy, isolating the trig function. So I get sine of theta equals a half. Now we're going to solve this as if we're on the unit circle. So what that means is that I'm finding the two places where the sine equals 1/2. So here's y equals 1/2. And the two angles that intersect at are pi over 6 and 5 pi over 6. So now I say that theta equals pi over 6 plus 2 pi k, that's going to be my general solution, or theta equals 5 pi over 6 plus 2 pi k. But I'm not done because I wasn't actually supposed to solve for theta, I was supposed to solve for y. So now here comes my back substitute step. So for my back substitute step, instead of theta, I'm going to write 2y. In fact, I'm just going to cross the theta out. So to finish solving for y, I need to divide both sides by 2. So y equals pi over 12, because I'm really multiplying by a half, plus pi k, or y equals 5 pi over 12 plus pi k. This is my general solution. So I could say set of y such that y equals all of this, and that would be my general solution. We're going to go ahead and just say that that's good enough. We've got the idea. Now the problem actually asked me to solve in 0 to 2 pi. When we're thinking about solving in 0 to 2 pi, we have to remember that this unit circle was for 2y. But we have now compressed by a factor of 2. So instead of there being 2 solutions, there's actually going to be 4 solutions in 0 to 2 pi. And here's how we can get the rest of the solutions. So our solutions in 0 to 2 pi. Our obvious first solution is pi over 12, because that is my first answer here. This is called the particular solution right here. And if I don't add pi k onto that, then I've got my first particular solution. My next particular solution is 5 pi over 12, and that's again not adding on a pi k. Okay, now the next solution, these two solutions correspond to k equals 0. These aren't really coterminal anymore, they are within one period of the function. My next two solutions are going to be from letting k equal 1. So if I let k equal 1, I'm doing pi over 12 plus pi, because I'm letting k equal 1, and pi is 12 pi over 12, so this becomes 13 pi over 12. And then 5 pi over 12 plus 12 pi over 12 is 17 pi over 12. And I could keep on going. So if you think about the work that's going on here, I was doing pi over 12 plus 12 twelfths of pi k, or 5 pi over 12 plus 12 twelfths of pi k. If I were to keep on going and add 24 twelfths, then I would be at 25 twelfths, which is more than 2 pi. So it would have gone outside of where we wanted to go. In general, whatever the compression factor is, in this case it was a factor of 2, that's going to tell you how many more solutions to expect. So I originally had 2 solutions, but then this doubles it, so I ended up with 4 total. So k equals 0 was my first set of particular solutions, and then I needed to do 1 more time. So I'm just going to show you quickly how you could solve this using Desmos. The first thing is that using an input variable of y doesn't really work. So we need to graph our original equation. The left-hand side was 2 sine of 2y, but we need to change our input variable name to x. So I say y equals 2 sine of 2x, and then the right-hand side of the equation was just 1, so I'm graphing y equals 1. And you can see that there are infinitely many intersections, but we want to concentrate on just the answers in 0 to 2 pi. So I'm going to use the gear up here, and I'm going to change my scale a little bit, and that's what you're going to see next. So here's the same set of graphs with my scale adjusted. So my x's go from negative 2 pi to 4 pi, and then I made sure that it showed up with scale factors of pi, and my y's go from negative 3 up to 3. And we can see that if I'm looking for our answers in 0 to 2 pi, then I'm looking basically for inputs between 0 and 2 pi. So here was my first particular solution, pi over 12, and then my symmetry angle was 5 pi over 12. Notice these solutions, one of them is as the function is going up and hits the line, and then the other one is as the function is going back down and hits the line. These solutions should be a full period apart from each other if you look for the same type of solution. So this is a distance of pi, which is the period when you have an omega of 2. So my next answer is 13 pi over 12, and 13 pi over 12 can be found by doing pi over 12 plus pi. And then my next answer that is also pi apart from this 5 pi over 12 is 17 pi over 12, so they're a distance of pi, and that was doing the 5 pi over 12 plus pi. Now I can keep on going to answers of 25 pi over 12, 29 pi over 12, 37 pi over 12, 41 pi over 12, and those would just be continuing to add pi to our previous answers. So if I do 13 pi over 12 and I add another pi, which is 12 twelfths, that takes me to 25 pi over 12. And then add another 12, that takes me to 37. But those answers are outside of 2 pi, so we were only looking 0 to 2 pi. They are answers in the general solution, but they're not in the restricted domain solution that we were finding. Okay, so let's look at another example involving cosine. It's the same basic strategy, except we have a z over 2, which is actually a stretch factor. So this will serve to, instead of doubling the number of solutions, this will actually half the number of solutions that you would expect. So again, we start with our variable substitution. So I'm going to let theta equal z over 2. So now my problem looks like the cosine of theta plus 1 equals 1. I'm going to rearrange cosine of theta equals 0. So there are 2 places where that happens on the unit circle. The cosine is the x-coordinate. It's 0 right here, where x equals 0. So at pi over 2 and 3 pi over 2. There's actually a compact way that we can write that as a single solution set. So we could say theta equals pi over 2. We could say plus 2 pi k. And then we could say 3 pi over 2 plus 2 pi k. But if we notice that these answers are really just separated by pi, an easier, more efficient way to do this would be to not require the second solution and just say pi over 2 plus pi k. Now this has nothing to do with the period of the function, it just simply has to do with the symmetry of these two angles, the fact that they're pi apart. Now I'm going to do my back substitution, so my theta actually equaled z over 2, and I will solve for z. Multiplying both sides by 2, so z equals pi plus 2 pi k. That would be my general solution. Now to find an answer in 0 to 2 pi, so my solutions in the interval 0 to 2 pi, there were previously 2 answers when we were considering on the unit circle. But this z over 2 is actually going to half the number of answers that I'm going to get. And so my answer should only be the first angle, or pi, because you can see to find other angles, we are going to add multiples of 2 pi. In this case, this isn't the period. It's half the period, but that's just had to do with the symmetry of these two answers. If I add 2 pi, then I'm going into 3 pi, and I've gone outside of where I want to look. So half as many solutions, instead of pi over 2 and 3 pi over 2, we're just getting pi. Okay, the next example has to, so our tangent in this case has an omega that is 4. So however many solutions we were expecting, we should get 4 times as many. We'll start by letting 4 theta equal some dummy variable, so maybe you want to call it phi or x or whatever you want to call it. So now my equation looks like tangent of phi equals 1. For the tangent function, we know that tangent is slope, so the slope is going to equal 1 here at pi over 4, and then also here at 5 pi over 4. But again, those are separated by a nice half rotation of pi, so we could write our general solution in terms of phi as just pi over 4 plus pi k. Now we back substitute, and we say 4 theta equals, and when we solve for theta, we are going to multiply both sides by 1/4. So we get pi over 16 plus pi over 4k. That is my general solution. Now notice that on a tangent, you don't ever have to find a symmetry angle because of the symmetry of the function itself. So there's my general solution, but now I actually need to find the answers in 0 to 2 pi. So the answers in 0 to 2 pi are going to start with pi over 16. My next answer, I'm going to repeatedly add pi over 4, and it might be helpful to recognize that pi over 4 is actually 4 pi over 16, just because we want to be able to easily add. So I'm going to add in 4 pi over 16. And I'm going to keep on doing this so long as I haven't left 2 pi, and 2 pi over 1 is the same thing as 32 pi over 16. So I just don't want to go over 32 sixteenths. So I'm going to add 4 pi over 16, I get 5 pi over 16. I'm going to keep on adding 4 pi over 16. So 9 pi over 16, 13 pi over 16, 17 pi over 16. Well, how am I going to know when to stop? I'm almost done. 25 pi over 16, and my last one, 29 pi over 16. Now, I had 2 solutions when I was just considering myself to be on the unit circle. So 1, 2, so at 3 pi over 4, and then 5 pi, not 3 pi over 4, sorry, at pi over 4, and then at 5 pi over 4. So here and here, 2 solutions. Now I was able to more compactly write that just like one solution because they were pi apart. So here are my first two solutions adjusted for the 4 theta part of the problem. So instead of pi over 4, it's a fourth of that, or pi over 16. And instead of 5 pi over 4, it's a quarter of that, or 5 pi over 16. So these are my first two initial solutions that I would have. This 4 theta quadruples the number of solutions I would expect. So here's 2 more, 2 more, 2 more. I had 2, now I have a total of 8. Now you can see that the next addition of pi over 4, or 4/16 of pi, would have taken me to 33 pi over 16, which would have been outside of the predetermined answer that we had there. So the basic strategy is to do your dummy variable substitution, solve like normal as if you're on the unit circle, back substitute, adjust your general solution, and then if they ask for answers in a particular domain restriction, usually 0 to 2 pi, you're going to run through different choices of this k in order to get all those solutions. It's helpful if you determine in advance how far you can go so that you know when to stop. And also you can use this omega to determine how many solutions you should expect. So that is how we are going to deal with period changes with trigonometric functions.